Okay, let us begin our today's presentation, today's class. In our previous class, we have discussed about the precision rectifier, right? We have started our discussion, in fact, on precision rectifier. What you can see here, I have already given you a brief introduction about what exactly is a precision device, right? Whichever is capable of processing the signal, which is generally very low in the magnitude. The voltage is very low in magnitude, right? So in such cases, we will be making use of the operational amplifiers along with the diode, and we have already seen how exactly you can materialize or realize the operation of a precision half wave rectifier with the help of this analysis in our previous class, right? So even we have gone through the design aspect of the precision half wave rectifier, right? So how would you select the different components as long as the precision half wave rectifier is concerned? And in that, basically, apart from the conventional things what we see, the selection of the diode here becomes an additional thing for us, wherein the diode is required to be considered with two aspects. One is the peak inverse voltage, right? That is the maximum reverse voltage which can appear across the diode, which should be generally double the voltage, either VEE or VCC, right? So I have already given you an example also. If your circuit operates or your operational amplifier is working with a supply voltage of 12 volts, then your peak inverse voltage across the diode, right? So PIV, so this will be your PIV, right? So it should be at least 24 volts. So that's what we have seen in our previous class. And apart from that, we have seen one more aspect, that is the reverse recovery time, TRR, the reverse recovery time. Yeah, this is what we have seen in our previous class. So it is the time required for the diode to go into the blocking state, right? So whenever there is a continuous switching between the open loop and closed loop in this rectification process, right? So the diodes should be given certain time for the recombination of the charge carriers. So that time should be at least equal to or greater than, so T divided by 10, where T is the time period of the input signal. These are the two aspects that we have seen in our previous class. And based on this, let us try to look into one simple example today. Let us note down the example now. Design a non-saturating design a non-saturating precision half wave rectifier. Design a non-saturating precision half wave rectifier to produce, all of you please note down, to produce a 2 volt peak output waveform, 2 volt peak output waveform from a sinusoidal input, of peak value 0.5 volts. Please look here, 0.5 volts, and a frequency of 1 megahertz. Use a bipolar op-amp with supply voltage plus or minus 15 volts, take IB max is equals to 5 microampere. Take IB max is equals to 5 microampere. So this is what is the problem statement. And as usual, you will have to draw the circuit diagram. All of you, please. Am I audible to all of you still?
Yes, sir.
Okay. Please note down the circuit diagram. You can draw on your own because we have already drawn it earlier. So let me take the things like this. Here I would connect the diode. And one more diode here. Then comes okay, so this I will join here, and this I can directly connect to ground. You can use one resistor also. This is R1, this is R2, D1, D2. So minus plus. So this is given to be plus 15 volts and this is minus 15 volts. These are the things which are given to us. So this is your input V in and this is your V0, and now here your V in and V0 are very clearly given. So this is what is my V in, and its peak value is how much? Input voltage 0.5 volts, and the input frequency is 1 megahertz. You know what for the frequency here would be used? So since it is an inverting type, you would have the output during this is V0 and its peak value is 2 volts. Okay, this is what you are supposed to observe here. All of you have noted down the circuit with input. So this is 0.5 volts. Output is 2 volts. Apart from or along with the rectification, the amplification also takes place, and it is almost 4 times. 0.5 volt is the input, 2 volt is the output, and accordingly you should be able to understand in what way you have to select the value of R1 and R2. And here this is my current I1. So bipolar op amp with a supply voltage of plus or minus 15, take IB max is equals to 5 microampere, right? Given IB max is equals to 5 microampere. IB max is equals to 5 microampere. So I1 for bipolar, we can take it approximately equal to 100 times IB max. So 5 into 100. So this becomes 500 microampere. All of you agree with me or not? The value of I1, $500 microampere. Okay. So this potential is a zero potential. This potential is also zero potential. Obviously, this will also be a zero potential by virtue of the virtual ground concept. So you can easily obtain the value of R1 now, which is equals to V in divided by I1. R1 is equals to V in divided by I1. So V in is 0.5 volts. I1 is 500 microampere. You can calculate the value of R1.
1 kilo ohm, sir.
1 kilo ohm. Fine. R1 is equals to 1 kilo ohm, right? So now this R2 you can find in two different ways, right? One is the gain is known to you, V0 by Vin, which is equals to 4. So obviously R2 will be 4 times R1. Otherwise also you can find out the value of R2 because most of the current will flow through this path as I1. So you know what is the value of V0. So you can find out R2 is equals to V0 divided by I1 approximately, except small biasing current there. So this is V0 is 2, this is 500 microampere. So this will be obviously 4 kilo ohm. The other way also you can calculate the value of R2 because our gain here is 4. Okay. And here, okay, so I have directly grounded it, the resistance. If at all you have some R3 here, if at all you consider R3 can be considered as R1 in parallel with R2, the biasing resistance. Okay, so this will be approximately equal to R1 only, right? You can take it 1 kilo ohm. That is basically this resistance is used to have the equal voltage drop whenever. So that is basically when there are internal transistors, right? Whatever the bias current you are going to give, the base current, they should be equal. In order to make sure that the currents are equal, outside you would like to have the equal potential difference. So that is the reason why we are using this resistance sometimes. Even if you do not make this resistance also, for a certain operational amplifier it works, right? You can always take the biasing resistance which is equal to R1 here, right? So this R1 or very specifically it is the parallel combination of R1 and R2. So you can take it as R1 here now, which is equals to 1 kilo ohm. Then I think these are the three things. You don't have anything else, but now you will have to go with the diodes. This is very important, right? So diode design with respect to the diodes. So first one is the peak inverse voltage. Simple PIV should be equal to or greater than plus VCC minus of minus VEE. So this should be equal to or greater than how much? 30 volts. It should be equal to or greater than 30 volts peak inverse voltage. Then the second one is reverse recovery time, which we call it as TRR, reverse recovery time. So TR, maximum reverse recovery time we can take, it should be greater than or equal to T divided by 10, which I have already told you. So F is 1 megahertz, so T equal to 1 divided by F. So how much is the value of T? 1 microsecond. Please check. 1 divided by 1 megahertz. 1 meg.
Yes, sir. Yes, sir.
So this should be 1 microsecond divided by 10. So it should be greater than or equal to 0.1 microseconds. 0.1 microseconds. Is that fine? All of you are able to understand this? Any doubt or any difficulty here in this problem?
No, sir.
Okay, fine. So with that we will move ahead with the next configuration, that is the precision full wave rectifier. Right, you have already studied the full wave rectifiers and half wave rectifiers using your transistors, even the diode configurations, right? So now we will try to see how we will be able to realize the operation of precision full wave rectifier. Precision full wave rectifier. First, let me draw the circuit. All of you please copy down the circuit. Look how the things change here, because whenever a particular circuit is being drawn here, maybe that appears to be simple, but when there are so many circuits you have, especially when you prepare for examination and all, so let there not be any confusion. In order to avoid the confusion, please try to understand how the things are arranged. Okay, one diode here and another diode here. And look here. You have this connection. There is resistance here. There is a resistance here. Then you will move ahead here, because in full wave rectifier obviously we need two op amps. So this will be your output point. Plus minus, this is one resistance and this is one more resistance. So this is V in. All these resistances we have taken it to be R. So this we call it as D1, this as D2. All other things you can write on your own, plus VCC minus VEE. Let me call this as amplifier A1 and this as amplifier A2. This is your V0. All of you please note down the circuit diagram. The operation of D1 and D2 depending upon the input signal. Suppose if I take this as the input, V in T, full wave rectifier, you cannot have the polarities, right? It will be giving you the output as per please draw these dotted lines. That gives the proper idea about how the rectification takes place. This is your V0. Please note down. All these things are clearly visible to you, I hope. Is there any confusion?
No, sir.
Okay. Okay, so this is the circuit. Now, the analysis of the circuit is based on, see, when the input is positive and when the input is negative. Okay, when the input is positive and when the input is negative, right? So based on those grounds only we will try to have our analysis, right? So let me take the first case, case 1, right? How would you get this output? That's what we are supposed to see here, right? When Vi is greater than 0, or V in, what we have taken here, it is greater than 0, right? So now please try to apply your mind here, right, to understand this. When V in is greater than 0, what happens? The inverting side, okay, so this one minus the first operational amplifier, right? So it will force its output. Its output means it is here, okay, A1. So this will make the output to go to the negative side, obviously, because it is an inverting amplifier, right? So when the output is negative, that means this terminal will be minus. So the diode D1, so this minus is connected to the cathode. Obviously your D1 will be forward biased and D2 will be reverse biased. This is what you are supposed to see, right? So when V in is greater than 0, output of A1 is negative, that is inverting. So this will make your D1 forward biased and D2 reverse biased. D1 is forward biased, D2 is reverse biased. Okay. Now when D1 is forward biased, so your circuit is completed here itself. No current will flow through the second operational amplifier here. So this potential and this potential will be same, it will remain same. And now because of this particular condition, that is when your D1 is forward biased and D2 is reverse biased, you should be able to draw the equivalent circuit here, right? So equivalent circuit means what? Under this circumstance, how the circuit behaves. This is my R1 here, right? Or R, all I have taken as R's only. And now when the diode D1 is conducting, I will just put it with a short circuit here, D1, like this, right? So D2 is open circuited, so this is connected to ground. D2 is open circuited, so when D2 is open circuited, your this R doesn't come into picture. So now this is a short circuit path, so therefore one more R, that is this R, I will bring here now. Okay, so this R is brought here, and my next op amp would look something like this. Now please check. So this is going to be your V0 minus plus minus plus. This is your V in R, R, R. All these things are R's only. So now from this circuit, okay, when as long as when all the resistance are equal here, your V0 is equals to V in. Let me call this as equation number 1. V0 is equals to V in, right? So what happens here when your output or when your V in is greater than 0, right? D1 acts as a short circuit, I mean it is forward bias. D2 reverse bias, open circuit. Your circuit would look something like this. This is called as equivalent circuit, and as long as the values of R are equal here, you will have V0 is equals to V in. So therefore this condition, this V0 is equals to V in when your V in is greater than 0. This is D1 on, D2 off. Okay, this is the first case. Now let us look into the second case, case 2. Let us look into the second case, case 2, when V in is less than 0, when V in is less than 0. So when V in is less than 0, again I need not explain the same thing. Your D1 will be now reverse biased. D1 is reverse biased and D2 is forward bias. All of you are following it or not, right? So when V in is less than 0, right, you have D1 reverse bias, D2 forward bias. So when this is the case, now we will try to draw the equivalent circuit. Okay, so how would you draw the equivalent circuit here? So my first op amp will remain as it is. This is my R1, and now you can see here what happens here, this output. So this path will now get opened, right? So this is connected to ground, and this point would have R coming into picture because my second diode now is acting as a short circuit. Now the see here, when this D1 is open, these two resistors are now in series, that will become 2R. Okay, these two resistances are in series, that will become 2R. So therefore what I will have here is 2R, and this will go here to the op amp, second op amp, and this will be R as it is. This is V0. This is R, this is R, this is 2R, this is your V in, and that is your V0 minus plus. Please check this. This is equivalent circuit. For the second case, when your V in is less than V in is less than 0, right? So now in this case, right, we will have the analysis now. Let the output voltage of A1, that is, this is your A1, this is your A2, let the output voltage of A1 be V volts. Let us say that this voltage is V volt here, or this point, both are same. Okay, and when this voltage is V, the differential input here, so that is this point and this point, so the differential input for A2 is equals to 0. The differential input for A2 equals to 0. That is quite understandable, correct or not? So that is the principle from which we have taken so many things, right? So V0, when this is the case, your V0 we have is A into VID. So that is your this V0, let me call this as VID. A is the open loop gain, as you know, A is open loop gain. Okay, VID is the, of course, the differential input voltage, so that is VID is equals to 0, right? V0 is the output voltage, and generally the value of this open loop gain A, which is very, very high for any operational amplifier, right? Since A is very high, so VID tends to 0. Since A, actually speaking, it is infinite, right? So when A is infinite, obviously your VID is equals to 0. Where since A is very high, your VID tends to become 0. Okay. So now from this, let us proceed further. The differential input to any operational amplifier, as we know, it is 0. So obviously when the differential input to the operational amplifier is 0, the input here, so now what is this voltage V? You can see here in this, okay, this is V. So VID should be 0, means this voltage also should be equal to V. That is, the input at the inverting terminal also should be equal to V. Okay, so what I will write here, this voltage I will write it as V. So this implies the voltage at the inverting terminal voltage at the inverting terminal is equals to V, since VID is equal to 0 and input at non-inverting terminal is V. Okay. Now, when that is the case, so now what we have taken, V here, this point, this is also V. Okay. So when these are the things, let me call this point as A now, small a. All of you look here. I call this terminal as A. So now I will start applying KCL at node A, right? Applying KCL at node A, applying KCL at node A. So if you apply the KCL at node A, now let us say that this is the current here, this is V, the terminal at A or the very A terminal is at 0 potential, so therefore the current will come from here, this is V. Okay. Now this is another path you can see here, so the current will flow here, right? So there is one more R. So how do you apply the KCL? Can somebody tell me now here quickly? This is if you consider this point, the current is entering here, the current is entering and the current is entering. Can you give me the expressions for the current here? Can somebody give me the expressions for the current here? The first current is what? This side, V in divided by R. Am I right?
V divided by
Yeah, V in divided by R, that is the first current, plus V divided by 2R. V divided by 2R, this is the second current, plus V divided by R. Am I right? V divided by R. So algebraic sum of the current is equals to 0 here. Algebraic sum of the current is equals to 0. So now what you do here is simplify it, get me the expression in terms of V and VI. All of you please try this, V and VI. So this becomes VI by R. You take that VI by R to the other side, so that becomes 3 by 2 V by R. Please check. 3V divided by 2R is equals to minus V in divided by R. Am I right? Or your V is equals to minus 2 by 3 into V in. Let me call this as equation number 2. Please check whether you are having the correct answer or not. V is equals to minus 2 by 3 into V in. V is equals to minus 2 by 3 into V in. Now see here in this diagram, whatever I am showing with the green color, V in, V and V naught. We have to relate V in and V naught. So we have related V in and V now, and next V and V naught are to be related. Okay. So for that I have to draw the equivalent circuit for this portion, I mean the second operational amplifier, right? If this is over, I will go to the next page. Shall I?
Yes, sir.
Okay. So now to obtain V naught, in terms of V in, consider the equivalent circuit for op-amp A2. Consider the equivalent circuit for the op-amp A2. So how does your circuit look like? I have one op-amp here. This is my A2. See here, I have 2R, I have R here, then comes your V0. This is your V0, this is R, this is 2R, this I am going to ground it, and this point also I am going to ground it. So this is my V, this is my A2. Please check. Only I have considered the op-amp A2. Okay, so now I will relate V0 and V using your simple voltage division theorem. Use voltage division theorem to get V0 in terms of V. Quickly, somebody. This voltage is the total voltage into resistance of the same branch divided by total resistance. So V here in this case is equals to V0 into 2R divided by 2R plus R. So this should give you V0 3 by 2 V. Am I right? Please check. V0 is equals to 3 by 2 into V. All of you are able to listen to me?
Yes, sir.
Okay.
Yes, sir.
V0 is equals to 3 by 2 V. Am I right?
Yes, sir.
Okay. Now you substitute this value in our previous equation where we had V is equals to minus 2 by 3 into V in. So we have V0 is equals to 3 by 2 into minus 2 by 3 to V in. So V0 is equals to minus V in. But we have gone with the double inversion here, right? Because I will go back 1 second. I will go back to this. So there is one, sorry, where is my circuit? Yeah, it is here. Okay, so we have one inversion here at A1. We have got one more inversion. So because of the double inversion, we are going to get the output V0 is equals to V in because of double inversion. So now the summary here, when V in is greater than 0, V0 is equals to V in. When V in is less than 0 also, your V0 is equals to V in. When V in is greater than 0 or when V in is less than 0, invariably your V0 is equals to V in. That gives you the function of full wave rectifier. It will consider only the magnitude of the input signal, not the polarity. So here your output this is when 1, this is 2, 2 is D1 off and D2 on. So this repeats and you are going to get the output as per the requirement of a full wave rectifier. Now after having seen this, please check, apart from the rectification, will it be possible for us to have the amplification as well, as I said earlier. So in this case we are using all the resistance equal to R, right? Suppose if you use this resistance, okay, something different, then definitely it is possible for us to have the rectification as well as the amplification. And you can try the same problem which I have given for the previous case, that is the half wave precision rectifier. I think design a non-saturating in the sense it is a precision rectifier only. It will not go and saturate at a particular value. It is also called as non-saturating, right? Design a non-saturating precision full wave rectifier, right? Maybe to produce a 2 volt peak from a sine wave of input peak value of 0.5 volts. The same frequency you can take 1 megahertz, right? And you can use the same bipolar op amp with plus or minus 15 volts, right? So you can try that problem, and that is only off the record, not now, right? If at all you want to rehearse one more example, please take it for the precision full wave rectifier. But only thing is that you have to make use of two devices here, I mean sorry, operational amplifiers, and accordingly you will have to select the value of the feedback resistance R differently, cater to the requirements of the gain parameter there. Okay, this is what you are supposed to look now.